we have the second part of Monique lecture. Now, please, Monique.
Okay. So good morning, everybody. So indeed, I will go on with the lecture. So yesterday, we discussed polynomial optimization, and we saw application or relation to detecting quantum entanglement of quantum states. And today, I want to move on to polynomial optimization, but now with non-commutative variables, and we will see how this can be used to model optimization problems dealing with quantum correlations. And the nice thing is that you have already heard some of these concepts yesterday in the lecture by Omar. So you will recognize some of the concepts. I will recall them, but some of the concepts you have already seen yesterday. Okay, so let's get started. So indeed, so this is the plan. First, to cover polynomial optimization in non-commutative variables and the use in quantum information. We will see how to design SDP hierarchies for approximating the entangled value, the quantum value of non-local games, and the maximum violation of Bell inequalities. So first of all, what is non-commutative polynomial optimization? So here is what is a typical instance of non-commutative polynomial optimization. So let's go over it. So we are now dealing with polynomials which have non-commutative, abbreviated as NC, variables. And the point is that we have n variables, x1, xn, you can look for instance here, but now these variables, instead of evaluating only at scalars, like yesterday, we are going to evaluate them at matrices or at operators. So this is why these variables should be non-commutative, because product of matrices or operators is in general non-commutative. So how does the problem look like? First of all, what are the constraints? I see here constraints saying that you have a polynomial hj, which evaluated at let's say a matrix tuple, x is equal to x1, xn. So hj of x should be positive semidefinite. So this is a positivity, this defines a positivity region. The visible region consists of matrix tuples whose evaluation at hj should give a PSD matrix. What is the objective function? So we have a polynomial p, which we also evaluated this matrix tuple. So we get a matrix, p of x is a matrix. And then if we want to minimize something, we should minimize a number. So what we do is we pick a vector psi, and we do the psi star p of x psi. So here I denote by this bracket, this is the inner product over the Hilbert space H. So let's summarize again. So what are the variables? First, we have a Hilbert space H, which can be finite or infinite dimensional. Then we have this vector psi, which is a unit vector in the Hilbert space. And then we have x1 up to xn, which are bounded Hermitian operators on H. So this is this symbol B star of H denotes a set of bounded Hermitian operators acting on H. So linear Hermitian operators which are bounded. So if H is finite dimensional, then these are just Hermitian matrices. So in this way, the objective function here is it's a number, and we want to minimize it over all tuples and tuples x of bounded Hermitian operators on H, and you optimize over H, and you also optimize over psi. And the polynomials are polynomials in non-commutative variables in x1 up to xn, and the non-commutativity is referred by the use of this symbol here, this curly symbol, if you wish. And they are assumed to be symmetric. I'll come back to this later. But if you have a product of two variables, x1, x2, you can take the star of it, which will be x2, x1. So this star you can think of being like the adjoint. It's the analog. This is the abstract analog of the adjoint in the complex case, or of the transpose in the real case. It's permuting the order of the variable. So a first observation is that which has been made. So we have seen such an instance of program yesterday in the talk of Omar. And as already observed, this is actually an eigenvalue minimization, because if you want to minimize this quantity here, this amounts to computing the largest lambda for which P of X minus lambda identity is PSD on this big feasibility region here. So this is the smallest eigenvalue of P of X. And what is this feasibility region here? I denote it by K infinite. So this is the union over all Hilbert spaces. Once you have a Hilbert space, you pick an n tuple of Hermitian bounded operators, and you pick all those X which lie in the feasibility region, which make Hj of X PSD. So this is the non-commutative polynomial optimization, the constraint one. So is there any question about the problem?
Questions? Yes.
Is there any way we can deal with non-symmetric polynomials?
So in this talk, I want Hermitian matrices because I want to have this, here I want to get a Hermitian matrix. So if the X are Hermitians and I apply a symmetric polynomial, I get a Hermitian polynomial. But if you would have equations, Hj of X equal to 0, you can also capture this, and then you don't need to require that the polynomial is symmetric. Okay, so before moving on how to solve these problems, let me first discuss how these type of problems can be used in quantum information, and namely to model so-called non-local games. And we have seen yesterday a typical instance of a non-local game in the lecture by Omar, but I will now describe it in a bit maybe more generality. But the quantum channel coding setting of Omar was an instance of, I think. It fits into this framework at least. So we will re-see a number of notions. So typically a non-local game would be, this is a cartoon which is representing a non-local game if you wish. So we have a big quantum system with two subsystems. This is Alice, the subsystem of Alice if you wish. Here is Alice, here is Bob. They are living on two different planets, which means this is supposed to symbolize the fact that their quantum systems are physically separated, their subsystems are physically separated, and they are doing measurement on their part of the system, on their sites, locally. Each of them is doing measurements, and then one wants to see what is the output of the measurements, and one will make a difference whether there is some entanglement which is taking place between the two players, Alice and Bob, or not. So here is a second cartoon which is representing how a non-local game goes. We have Alice, we have Bob, we have the referee who is sitting here, and the referee is sending a question to Alice, S, sending a question to Bob, T, which he picks a question with a probability, and then Alice should reply, send an answer A to the referee, Bob should send an answer B to the referee, and then the referee looks whether their answers are correct or not by looking at some predicate which defines the winning strategy of the game. And Alice and Bob may use some kind of strategy which may be classical or quantum. And when it is a quantum strategy, they use a so-called quantum state, psi. So this is supposed to represent this quantum state, which is playing between the two players. So this is a cartoon, and now I will present the definition in mathematical terms. So what is a non-local game? It is specified by two sets of questions, S and Alice, S for Alice, T for Bob. Pi is a probability on the pairs of questions. Then Alice has her own answer set A, Bob has his own answer set B. And we have a function V, which is called the predicate, which is going to indicate when is an answer good or wrong. We have two players, Alice and Bob, and the referee. So, as already said, how does the game go? So this is a one-shot game. the two players may agree on a strategy before starting the game, but they don't communicate during the game. Now the game starts, so the referee chooses a pair of questions ST according to some probability pi. He sends question S to Alice, question T to Bob. Alice answers A, Bob answers B to the referee. And for this, they use some strategy which I have chosen before the start of the game. And then there is a certain probability of getting answer AB to question ST. Let's call it P of AB given ST. And this probability, no, okay. First, there is a predicate then, V, which is a function which to a quadruple answer A, B, question S, T, maps a number 0, 1. 0 means failure, 1 means winning. And the fact is that Alice and Bob win the game only when their combination of answers to the question has predicate value 1. So 1 indicates that they have answered correctly to their questions. 0 would answer that they indicates they have answered wrongly. And then one is interested to finding the maximum probability of winning the game. So this probability is defined by this expression here. We sum up over all the questions with weighted by the probability of the pair of questions. Then we sum up over all the questions. We only take into account over all the answers, sorry. But you only take into account in the summation those which have predicate value 1. If the value of V is 0, then this doesn't enter, but this is the way to write it in general. And then for all those which are correct, then we sum up the probability. So this expression here, it's a linear expression in terms of this probability term P. And we want to maximize this linear objective function in terms of P. So let's write it. It's a linear in P, so we can write it as the inner product between a certain constraint C, comma P. And here P, what is it? We optimize over all probabilities which lie in a certain set script P, which will be the given set of strategies that Alice and Bob are using. So winning probability of the game is this optimization problem. It's an LP over this set P. It's a linear programming problem over this set P. So we saw already yesterday in the talk of Omar such the probability of success for the quantum channel coding problem. So now let's see two kinds of strategies that Alice and Bob may use. First classical and then quantum. So first classical. What are classical strategies? Let me maybe say ahead, the most simple thing one can think of is that there is no probabilistic at all. Alice and Bob just do a deterministic choice. Before the game, they choose function from their questions to their answers. Bob chooses also a function from his questions to his answers, and then when they start the game, they just answer according to the functions they have decided upon before the game started. That would be a deterministic strategy. And in a nutshell, what are classical strategies? They will be simply convex combinations of deterministic strategies. But okay, let us now go how it would be introduced usually in the quantum information literature. So how it's said is that Alice and Bob determine their outputs or their answers by employing so-called both private and shared randomness. So shared randomness is simply that they can toss a coin. They have n possible options, say, and they toss a coin to decide, okay, I'm going to follow option I with probability lambda I. So this is something they do together. And then they have shared private randomness. So Alice, so now let's fix that they have chosen the option I. So let's not look at I anymore. But when Alice gets question S, Alice has a probability distribution about her set of answers. So she has numbers XAS, non-negative, and summing up to 1 when you sum up over the answers. For every S, if you sum up the X AS, you get 1, and these numbers are non-negative. So it's the probability about her set of answers for every possible question. And the same for Bob. He has a probability YBT about his answers for every T, for every question T. And then the probability of answering AB is defined by taking the product XAS times YBT. And here, since there was this shared randomness, you sum up over all I multiply times lambda I times this quantity. So any correlation which is of the form, like I just explained here, is called classical. So such classical correlation from a polytop. So easy to see, this is a polytop and it's denoted by C index log. So this log stands for local because the whole course of action is defined locally by Alice on her side and Bob on his side. And the vertices of this polytop are exactly the deterministic strategies which I mentioned a few minutes ago. So where Alice has a function from her questions to her answers, Bob has also a function from his questions to his answers, and the probability would be just 1 if Alice answers according to a function, and the same for Bob. So the vertices are 0, 1 valued, and the classical correlations are convex combinations of these 0, 1 valued things. So it's a very combinatorial object. So if we have a polytop, so this classical, the set of classical correlations, C log is a polytop. So it has faces. Every face is defined by an equation. And this equation corresponds to the so-called Bell inequalities, which were introduced by Bell in '64. So a Bell inequality is nothing but an inequality of the form. So I don't know if I have it here. This would be an inequality of the form C in a product CP at most, the maximum over the set of classical. So CP at most omega C, where this omega C is defined as the maximum value. CP at most omega C is a Bell inequality. So one is interested in understanding what is this maximum value over the set of classical correlations. This is denoted omega C, C for classical. And this is a classical value of the game. And this is, you can just compute it as a linear programming problem in principle. But this is difficult because this polytop has exponentially many vertices and the facets also are very difficult. So exponentially many of them and mostly unknown. So computing this classical value is, in general, an NP-complete problem. This would contain such a problem like maxcut is in disguise contained in it. So I will now move to, so this was classical strategies, and now let's describe what are quantum strategies. So in the quantum setting, Alice and Bob share a quantum state, psi. So there is again these two Hilbert spaces, HA for Alice, HB for Bob. I choose them here finite dimensional, and they share a quantum state, which is a vector lying in the tensor product. And before, Alice had private randomness, which was having a random probability, having this probability XAB on her possible set of answers. Now this is the analog of this now is having matrices. So instead of the little scalar XAS before, now we have matrices, which I've now denoted by A, indexed by the answers and the questions of Alice. So AAS is PSD, Hermitian PSD, and they sum up to the identity when you sum over the answers. Such a thing is called a POVM, which stands for a positive operator valued measurement. So positive operator valued, because these A's are matrices, are operators, and a measurement. So using these things, Alice is going to use this to make a measurement on her part of the system. The same for Bob. Bob has such a POVM, now denoted B's, with matrices B, PSD, summing up to the identity when you sum up over the answers for every T. And now, what is the probability of answer AB? It is given by this formula. You take the inner product, which is a vector psi, so the quantum state, with, so now you do the tensor product of the operators of Alice with the operators of Bob, which you apply to psi. We have seen this expression before. And the quantum value of the game is optimizing, so that's the same objective function as before, but now for P, we choose the quantum definition of the correlation P, which is put here. So we optimize this this objective function over all possible Hilbert spaces, HA for Alice, HB for Bob, psi, and these are the A's and the B matrices for Alice and Bob. This is the quantum value of the game. And if we look at the set of quantum correlations, these are all the P's which are of the form of that form, for some psi, for some A's, for some B's. Then they form a convex body, CQ, for C for the Q for quantum. So that's a set of quantum correlation. And this is a convex body. It is bounded and it is convex. So convexity, I advise you to do this as an exercise, that if you take two such correlation, if you take a quantum convex combination of them, that you get again a quantum correlation. And this is where you have the freedom of using different Hilbert spaces. But it's a nice exercise to do. If you would restrict your Hilbert spaces to have each of them having dimension 1, then you would get back numbers here. So you would get back to the classical case. So every classical correlation is a quantum correlation. So C log is contained in CQ. So the quantum value is larger in general than the classical value. A small observation is that you need to choose value state psi if you want to get a quantum correlation P, which is not classical. Because, for instance, if your state psi would be a product state, then the correlation you get is actually classical. And why is this? Because if you spell it out, if psi is a product here on both sides, you take a product, and this big inner product here splits up as a product of the two separate inner products. So, and this is precisely the shape of a classical correlation. So we find again that if psi is a product state, then we get a classical correlation. And so if we want to get a true quantum correlation, we need to select psi which are not product states. So the psi should be and give rise to an entangled state. So more generally, what you could do is to define your correlation P by moving, so the psi here, I move it on the other side, and I would get the inner product of this matrix times psi psi star. So in other words, inner product of the matrix with a row of the form psi psi star. But you could also take any row which is separable, and then this would also give you a quantum correlation which is classical and which is quantum but classical. So if you want to get a true quantum correlation which is not classical, you need to select a row which is not separable. So just to make the link again with what we saw yesterday about the set of separable states. So if psi is a product state, then we get a classical correlation, so nothing new. So, but if psi is not a product state, then it is possible always to create non-classical quantum correlation. So it is possible to find A's and B's. That gives quantum correlation. Oh, so maybe it's a good point to stop and ask if there are questions about these definitions.
Do we have questions?
So it seems
No.
no. Okay. So now the whole game is to understand what is the difference between quantum and classical. Are these values the same, maybe sometimes, or different? So, but let's see some examples of non-local games. So a classical class of non-local games arises from the so-called XOR games. So in a sense, the most simple one can think of. So answers are just two possibilities, 2 bits, 0, 1. And the predicate function is defined in this way. We have a 1 precisely when the XOR of the answers, A plus B, is given by a function of the question. So we have a function f, which to every pair of questions assign also 0, 1, and then the predicate is given is equal to 1 if the XOR of AB is equal to the function of ST. So this defines now fully a non-local game. And the very beautiful result by Chirelson says that computing the quantum value of an XOR game, such a game, actually this can be done efficiently using a semi-definite program. So it's a very remarkable result that computing the quantum value, which is this optimization over all Hilbert spaces and a very broad range of possibilities, actually it boils down to one single semi-definite program. This is exploiting the shape of the predicate and of the question answers sets. As a very, very special case of an XOR game, there is a CHSH game due to these authors, where now also the questions are two possibilities, 2 bits, 0, 1. And the function of question pair ST is just given by S times T. And then it can be checked that the quantum value is equal to this number, which is 0.85 approximately, by solving this SDP. I mentioned that the quantum value can be, so you can compute it exactly, this SDP, you get this value. On the other hand, the classical value is equal to 0.75. And the classical value here amounts roughly to computing a max cut of a certain associated bipartite graph. So we see that there is a separation between classical and quantum value. And that's nice because this is showing existence of entanglement. So there are quantum correlations which are not classical, which gives a larger quantum value of the non-local game. So this showcases entanglement. So the summary for XOR games, computing the quantum value is easy. It's just an SDP. And actually, this will be the first SDP in the hierarchy of SDP relaxations, which we are going to present next. It just happens that for XOR game, the first level of the hierarchy is already good enough. On the other hand, computing the classical value is hard because it relates to max cut. But this is exceptional, that computing the quantum value is easy. This is true for XOR game, but in general, it's hard for general games. So maybe I mention one other kind of games one can look at, which has been looked at in the literature, still with the aim of understanding how far, what is the advantage of using quantum resources versus classical. This is a so-called coloring game. We have a graph and a number k, which is the available number of colors we can have to color the vertices. And then the question would be, can one color the graph with k colors? Where classical coloring should obey the following rules, that if you have 2 vertices which are adjacent, they should get distinct colors. And of course, a vertex can get at most 1 color. So here the questions would be the vertices, and the answers would be the k available colors. And the predicate would be that the value is 0 if, so you get this value is 0 if, so A and B are the different, if you have 2 distinct colors, so this is saying that 2 distinct colors cannot be assigned to a single vertex. So that's logical. And the second one is saying that if two vertices form an edge, then they cannot get the same color. So these are, the predicate is designed in order to model a proper coloring of the graph. And then you may call chi star of G would be the minimum K for which there exists a so-called perfect winning strategy. That means a strategy with value 1, which would mean that you never select, you never make a decision which correspond to predicate value 0. So if you would start, if the star here would be the lock, if you would optimize over C lock, the set of classical strategy, then this coloring parameter here would be exactly the classical coloring number that we all know. But we can now define, so this is the classical coloring number, and psi Q would be the quantum coloring number, the minimum K for which there exists a perfect winning strategy in the set of quantum strategies. So we always have this inequality. If you use quantum strategies, the coloring number can be lower. And interestingly, actually, it can be exponentially lower. So there are examples of graphs, classes of graphs with showing an exponential separation. So this really means the advantage of using quantum entanglement. So this is just very roughly saying, and there is quite some literature about quantum analogs of other graph parameters. And as another example, there is a quantum channel coding problem, which we saw yesterday in the lecture by Omar. Good. So I have introduced non-local games and explained what is a classical value, what is a quantum value. And now let's see how can we compute this quantum value, or how can we approximate it. So here I've just repeated what is quantum value of the non-local game. This is objective functions when you optimize over all these things here. And this doesn't quite fit in our framework of non-commutative polynomial optimization, which I explained on the first slide, because in the first slide, when it was an expression of the form psi, comma, p of x times y. So there, in the middle here was a polynomial in a number of variables. But here we see a tensor product. So that's a difficulty. And what is the first step is actually to remove these difficulties, this tensor product, by introducing new variables. Let's introduce a new variable in blue, which is, I denote E, which is the tensor of A with the identity. And F in blue is the tensor product of identity with B. And then it's obviously the tensor product of A and B is equal to the product of E and F. So by introducing this new variable, I've removed the tensor product, and I now have a true good product of two matrices E and F. Now these E and F are matrices, operators acting on a bigger space, acting on the tensor product of both. But the objective value here is of the desired form in the non-commutative optimization problem. It's a psi times a product of two variables with psi. Let's see what these new variables satisfy. They are again PSD, they again are P of EM. They sum up to identity when you sum over the answers. They have an additional property, which is a so-called bipartite commutativity. E and F commute. E times F is equal to F times E, because here we have this identity. So this is what is indicated with this commutator. So this symbol here should be read as EF minus FE. So for short, we write the commutator of EF is equal to 0. So this is an additional constraint that we can put on our variables. And then we can look at a new optimization problem, which you obtain by replacing the red part here by the blue part using the new variables E and F. And the optimization is over H, which is a Hilbert space. So now this H would play the role of HA times HB, tensor HB. Now I just have a single Hilbert space, a big one. Psi is a unit vector in it, and the E's and the F's are Hermitian bounded operator on H. So the only difference between the two problems is replacing the local A and B by global variables, if you wish, E and F. So let's give a name to the set of quantum correlations which arise in this way. Actually, now they are called quantum commuting correlations. Let's call them as CQC, the set, and this gives us a bigger set than CQ. By construction, it's clear that every quantum correlation is in CQC. This is exactly the construction shows this. So the quantum value is, in principle, at most, a quantum commuting value. And so these are these different sets of correlations that Omar was alluding at yesterday. So you may wonder, are these, maybe I should, okay, doesn't matter, I clicked too much. So CQ, the preceding slides was CQ, yeah. CQ is contained in CQC. And you may wonder, are these two sets the same or not? Are these two optimal values the same or not? And this has been long time open, but this is now quite settled. So the first thing you can observe is that the set CQC is closed because you are optimizing here. I didn't say explicitly, but this H can be anything, infinite dimensional Hilbert space. So CQC is a closed set. CQ is not apparent that it is a closed set because this is defined with these tensor products, and you assume, so it's not clear. So let's put the closure of CQ in between, like this. And actually, it has been shown a few years ago by Slofstra that actually CQ is not closed. So this first inclusion here is a strict inclusion. And then there was still the open question whether maybe the closure of CQ is equal to the CQC. And actually, this was recently disproved in this paper that Omar mentioned yesterday already, in conjunction with showing undecidability of computing the quantum value. So what they also show in this paper is that actually the closure of CQ is not equal to the CQC. So here we have also a strict inclusion. And there is a connection between this disproving this and the so-called Cohn's embedding conjecture. There was a result showing that the closure of CQ is equal to CQC for all possible A, B, S, T predicate, for all possible non-local games, if you wish. So this equality here for all possible settings of non-local games would be equivalent to the Cohn's embedding conjecture, which is a conjecture in operator theory. And it was open for a very long time, but okay, now this conjecture is disproved. And this here, it's a strict conclusion. Okay, so this is the setting. So we have introduced a new parameter, the quantum commuting, because now it's what we like with this new parameter is that it is a typical instance of a non-commutative polynomial optimization. So now let's move on and see how to approximate a non-commutative polynomial optimization. So was there any question before I move on?
Yes.
Could you go back to the example about the graph coloring, please?
Yes. Oh yeah, it's here. Yes, please, yes.
I think that's okay. I don't see. Oh, yeah, there. Sorry, I'm kind of confused about what it means that the quantum graph coloring is less. I mean, can we color the graph with less colors? I mean, what's the intuition behind it?
Now the intuition is actually this quantum number is using kind of very roughly said, you are optimizing, you are using more resources. So than in the classical case. So sometimes it may happen that you are more lucky in the quantum. So maybe another way I can explain this is, so now it's defined as the minimum K for which there is a perfect winning strategy P in the set of quantum correlations. Actually, there is an equivalent characterization of this quantum coloring number, which would be, so think about the coloring number. How could you view it? What you could say is you set up an LP where you have variable indexed by the vertices and the colors, and you try to check whether this LP has a 0-1 solution. You would have variable xi, variable which is equal to 1 if vertex I gets color k, say. So you get such a linear programming problem with variables x, which are 0-1 value, depending whether the vertex has a given color or not. So you can set such an LP. And the coloring number, the classical coloring number, would be the smallest k for which this LP has a 0-1 solution. Let's agree that such a thing is possible. It's easy to do. And then what would be the quantum coloring number? What you would do is take the exact same LP, but now instead of having only 0-1 valued solution, you would allow solutions which are matrices X PSD. And you would wonder what is the smallest k for which your system has matrix solutions. Then it's quite, if you accept, I think Webex is not accepting. Okay, resume. Okay, we're back. Do you see what?
Yes.
Do you see? I have a small. Okay, no, it's good now. It's good. So then, if you accept that with these alternative descriptions of the quantum coloring numbers, then you see that since now you are allowed to use matrices instead of only scalars, then you can much faster be able to satisfy your system, and then the quantum coloring number can be smaller. Does it make some sense to you?
I mean, I was kind of wondering what it means for the actual graph. Does it look different as an end result, or it's just? Okay, I mean, this helps a little bit. Thank you.
Your quantum colors.
Okay.
Okay. So I go back to how to approximate non-commutative polynomial optimization. So the strategy is going to build, just as in the classical case, strategy is to build SDP relaxations using sums of Hermitian squares and the dual theory of moment. And this has been pioneered by these two groups of authors, Asin Navasquez-Pironio, who especially stressed the moment approach. And there was another paper by Doherty-Liang, Toner-Wehner, where they especially stress the SOS approach. So usually now this hierarchy goes under the name the PNA hierarchy, according to the first authors. Okay, so some notation. As before, this symbol here denotes a set of polynomials in non-commutative variables, x1 up to xn. So like this is a non-commutative polynomial. So x1, x2 minus x2, x1 is a polynomial. It's not 0 because now it's non-commutative. This would be another polynomial, and this would be another polynomial. And this one is different from this one. Also, they use the same letters in the same frequency. Here we deal with, we instantiate two Hermitian matrices. So we assume xi star is equal to xi. And okay, so then I revise my answer to a question which was given in the beginning. Somebody asked whether we always need to assume that the variables are Hermitian. Actually, you can do the theory also for non-Hermitian variables, and you have to keep in your non-commutative polynomial optimization problem, you have to keep the xi and the xi star. So this theory is also developed also in the non-symmetric case. But for us today, variables are Hermitian. So xi star is equal to xi. But if I have a product, say x1, x2, x3, and I do the star of it, then this reverses the order of the variable. And we call a polynomial symmetric if p star is equal to p. So for instance, x1, x2, x3 plus x3, x2, x1 is symmetric. But this one, x1, x2 minus x2, x1 is not symmetric because if you take the star of it, you get minus the initial polynomial. Okay, so now what I want to do is to review a few crucial results which have been established about positivity of non-commutative polynomials. So one such very early fundamental result is due to Helton and McCullough, and it characterizes positivity. So let me maybe put already the three statements which are equivalent. So suppose we have a polynomial p which is symmetric degree 2d. Then the following three things are equivalent. The first one is saying that if you evaluate p at a matrix tuple, I should say at an operator tuple, then you get a positive element. And so here the xi are Hermitian bounded operators, and you allow any Hilbert space. This is the most wide thing you can do. The second one is a bit more restrictive. You only ask matrices, and on top of that, you ask your matrices to have a given size, capital D, which is given by this number. But so the 2 is asking that the positivity condition holds only for matrices up to a certain size, given size. So this is way more restrictive. The third option is saying that your P is the sum of Hermitian squares, which means that you can write it as a sum of fi star fi, or some non-commutative polynomial. So this is a remarkable result. This is saying that non-negativity is actually characterized by being a sum of squares. If you remember, in the commutative case, this was absolutely not true. We had the result of Hilbert, which said that being non-negativity being equivalent to being a sum of squares is a very rare phenomenon, only in 3 cases, degree 2, one variable, or a very special case. But in the non-commutative case, being a sum of Hermitian squares is equivalent to being to positivity, to non-negativity, over all possible operators. This is a very nice result. We'll see later some argument or some hint of an argument why such a thing could be true by going to the moment side. So as a corollary, on constraints non-commutative polynomial optimization, which is the infimum of this quantity without constraints. So this is actually a single SDP. This is a sup of lambda such that P of x minus lambda identity is PSD for, okay, this is given by this single SDP. So sup lambda such that P minus lambda is the sum of Hermitian square. So computing this minimum eigenvalue problem, which is given here, can be solved by a single SDP. So the problem looks more difficult because we're optimizing over such an immense feasibility region, but it turns out that you can actually solve it easier by a single SDP. So this is what we can say about an unconstrained case. Let's move on now to the constrained case, because this is the setting of non-local games or constraints. So now we have the constraints are given by this symmetric polynomial h1 up to hm. I recall the definition of the feasibility region, K infinity, so where you run up over all Hilbert spaces and over all possible tuple of bounded operators satisfying the constraints. And in blue, K is if I restrict myself to matrices instead of infinite dimensional Hilbert spaces. So this is a smaller subset of the K infinite. Now we can again define the quadratic module, which is defined by elements of the form a sum of Hermitian squares. And here we have the constraints H. And what we do is we pick a G and we pre-multiply by G star and we post-multiply by G. So in this way, this term here is symmetric. So this is a non-commutative analog of the quadratic module we saw yesterday. And an easy observation is that if we have a polynomial which is the quadratic module, and if you evaluate it at an x which is in this K infinite, then you get a positive element. This is why you use this fact here. And Helton and McCullough showed the analog of the positive Stellensatz of Putinar, in a sense. So under the Archimedean condition, which again reads as saying that there is an R for which R minus sum of xi square lies in the quadratic module. Under these conditions, and the following holds: if P of x is positive definite for every x in K infinite, then P lies in the quadratic module. So this is a non-commutative analog of the positive Stellensatz of Putinar we saw yesterday. And this is the key for showing the convergence, asymptotic convergence of the hierarchy. But okay, so now let's go to the defining the hierarchy. So here I've recalled the non-commutative optimization problem. We want to optimize this subject to the constraints. In other words, this is reformulation. In order to be able to get things that you can compute with SDP, we should truncate the quadratic module, which means that you simply restrict to the setting where the first term here has degree at most 2t, and here each term has degree at most 2t. This is a truncated quadratic module at degree 2t. And then we can define the SOS relaxation, P SOS t, which would be the largest lambda for which P minus lambda is in this truncated quadratic module. And as a consequence, for instance, of the result of Helton-McCullough, which I saw before, under the Archimedean conditions, these sums of square bounds converge asymptotically to the minimum of P. So this is the very exact analog of what was happening in the commutative case. But so asymptotic convergence under Archimedean condition holds. On the other hand, some things happen in the non-commutative case which are nicer than in the commutative case. And one such nice thing is, for instance, that for certain optimization, constrained optimization problems, and actually one can show finite convergence, which was not true in the commutative case. So this is true, for instance, for the matrix ball, if you have just one constraint, which is of the form 1 minus sum of xi square, or if you would look at the matrix hypercube, where you would say that you have n constraints of the form 1 minus xj square. So this would mean here that you are asking that your matrix solutions are contraction matrices, all eigenvalues between -1 and 1. So in each of these two cases, the SOS hierarchy I just defined actually has finite convergence. And let's see. So this is result of Kafuta, Klepp, and Poe. So assume that our feasibility region is a matrix ball or the matrix hypercube. In other words, either this constraints H or this constraints Hj here. And let's pick a symmetric polynomial P of degree D. And then what they showed is, the first thing they showed is that P of X is positive on K, if and only if it lies in the quadratic module truncated at degree D+1. So again, we have equivalence of being positive with membership in the quadratic module. And on top of that here, we even have an explicit expression for the truncation where P of the quadratic module in which P lies. This is the first. P has degree D, well, you just go to D+1. And this then in turn is equivalent to P being positive on the full region, K infinity. The first result. And as a consequence, the minimization over the matrix ball or the matrix hypercube can be computed via a single STP. This is a consequence of the first item. And what will, yeah, I will come back to this later. So this is a rather remarkable, I think, that it's a bit mind-blowing, at least when I first saw it, that suddenly for the matrix ball and the matrix hypercube or the unconstrained case, you have this equivalence of positivity with membership in the quadratic module, and on top of that, with a degree bound, with an explicit degree bound, which is much more, which is in general not true in the commutative case. And what actually is underlying these facts is, or at least in my view, what makes them makes it much more easier to grasp is by going to the moment approach. So now I will go to the moment approach to non-commutative polynomial optimization. So here it goes. So it will be, of course, the dual to the sum of square approach I just defined. But maybe let's start from scratch and let's again reason how does it naturally occur. Just like for polynomial optimization, the moment approach arose by saying I want to model a non-linear term x to the alpha by associating a variable to it, so by having a linear functional and replacing x alpha by L to the x alpha, we just do the same here. So suppose we have a solution h x psi to our non-commutative polynomial optimization problem, then we can define a linear functional L acting on non-commutative polynomials of degree 2t, say, to R. And this L is defined by simply L of a polynomial P is given by this expression. This is the exact analog in the commutative case. It would be L of P is equal to P of X. In the non-commutative case, you now take this expression. So you model all the terms which are difficult in your program by introducing a linear functional. And now let's see what are the properties that you can impose on this linear functional. First property is that L of 1 is 1, because if P is 1, then P of X is identity, and then you get the norm of psi, and psi was norm 1, so you get 1. So L of 1 is 1. L is symmetric. If you plug in a symmetric polynomial, L of F is equal to L of F star. L is non-negative. If you pick a polynomial in the quadratic module, then you get a non-negative number. So, for instance, if F was a sum of Hermitian squares, so if it was of the form Q star Q, then L of Q star Q would be psi Q star X, QX psi. So then this would be a non-negative number. And the same for with the constraints. So L is non-negative on the quadratic module. And then it's natural to define the moment relaxation of order T as the minimum of L of P, subject L of 1 is 1, and L is non-negative on the quadratic module, truncated at degree T. So the M should be a Q here. And you optimize over all linear functionals up to degree 2T, which are symmetric. So this is a very exact analog of what we saw in the commutative case. And this moment bound is a dual of the program defining the moment bound is dual SDP to the program defining the SOS bound. So the moment bound is nested between SOS bound and the minimum of P. So just to repeat, under the Archimedean condition, the SOS bound converges to the minimum, so also the moment bound converges to the minimum. But so we saw already a proof of asymptotic convergence via the Elton-McCullough result on the sum of square sides. So this is one way to derive it. Another way to derive the asymptotic convergence directly of the moment bound to the minimum would be to do the so-called GNS construction. So the GNS construction would give you a different proof of convergence, and on top of that, it would give directly an optimal solution to the minimum. So it would give an optimizer, if you wish, to the minimizer, to the minimum P-min. I will, if time allows, I will in a few slides try to give you the GNS construction to briefly recall how it goes.
Monique?
Yes?
So in the definition of the moment relaxation, you mean Q of H, no?
Yeah, I mean Q of H, yes. So M should be a Q, yes. Yes. It's a typo, thank you. Yeah, it should be Q, should be Q.
There is
a
question. In Helton's Positivstellensatz, there's no equality between non-negativity and being a module, but on one side we demand strict positivity. Is there any interpretation to that asymmetry, or are there any issues arising because of that?
So indeed, in the Positivstellensatz, it's not an equivalence. It's if P is strictly positive on the feasibility regions and P lies in the quadratic module. In the commutative case, was also like this. But it's not a trouble to use this result for showing the convergence of the hierarchy, because then you add a small epsilon, and but it's true, there is an asymmetry. It's P strictly positive implies P lies in the quadratic module. P lies in the quadratic module implies P is non-negative. Does it answer the question?
Yes.
Thank you. But again, you can use this result by adding to show the asymptotic convergence by just adding small epsilon. Huh? If you have a P non-negative, then P plus epsilon is strictly positive, and then you factor out the epsilon in the proof. So just like in the commutative case, we saw the flatness result. There is also a flatness result in the non-commutative case, and it goes in the same way, in a sense. So let's L be an optimal solution to the moment relaxation here. So L is acting on polynomials up to degree 2t. Assume it is flat, which means that the rank of the matrix, its moment matrix over the t is equal to the rank of its moment matrix of order t minus dk, where this dk is the largest half degree of the constraints. Then the relaxation is exact. So under flatness, the relaxation is exact. So the moment relaxation is equal to the moment bound is equal to the true minimum. And on top of that, one can construct an optimal solution to the original optimization problem. And the H here will have finite dimensional, and its dimension will be this rank R of the moment matrix. And the X here are going to occur from the so-called multiplication operators. So if time allows, I have a slide showing how this. So this proof goes again along the GNS construction, and if time allows, I show how it goes. So this flatness result is very interesting, and it also underlies the fact that in the unconstrained case of the matrix ball or the matrix hypercube, things were so nice that you had equivalence between positivity and sums of squares. So that's the next thing I want to say. So the flatness result is key to the finite convergence of the hierarchy in the unconstrained case, and also in the constrained case in some cases like the matrix ball or the matrix hypercube. It's not true always in the constraint case, of course. But if the constraints are tuned to satisfy certain nice conditions, then finite convergence also holds. And the key ingredient is lies in this result. So suppose we have an L which is positive, meaning its moment matrix is positive semidefinite, or equivalently L is non-negative on sums of Hermitian squares up to degree 2t. So this is, we have such an L. And the claim is that we can find another L prime, which has nicer property. In a nutshell, it's flat, and it coincides with L almost everywhere. So let's see. So the claim is there is an L prime, which acts also on polynomials up to degree 2t and satisfies the following property. The first one says that L prime and L agree on polynomials up to degree 2t minus 1. So the only places where they may disagree is on monomials of degree 2t. But everywhere else, they agree. The second property is that L prime is positive again. Its moment matrix is PSD, or in other words, L prime is non-negative on sums of squares. The third property, which is the most important one, is that actually this L prime is flat, which means that what's written here, so its moment matrix of order T has the same rank as the submatrix of order MT minus 1. So now, if we have this L prime, which is positive and flat, due to the result we just saw before, then we know that L prime has what I put into quotes, representing measure. So there exists a psi and an x. I didn't write, I should also have written an Hilbert base space of finite dimension such that L prime of P takes this form. It is of the form psi dot px psi for all polynomials up to degree 2t. So this comes from the flatness result. So this L prime is nice. It looks like we want it to look, but L prime coincides with L on degree 2n 2t minus 1. So we have the same for L when you restrict it to 1 degree less, up to degree 2t minus 1. And this fact, so where does this come from? In a nutshell, I didn't draw it, I should have drawn it, but the moment matrix of order T, it's a big matrix, yes? And here you would have the submatrix where you have the degrees up to T minus 1, and the lower below corner would be the submatrix indexed by monomials of degree equal to T. And if you look at the submatrix indexed by monomials of degree equal to T, the point actually is that there are no conditions on the entries. Being a moment matrix says nothing because the variables are now non-commutative. So if you have a moment matrix, you can modify the lower corner indexed by monomials of degree T in order to make it flat and positive. This is the key ingredient here. So non-commutativity is actually way easier to handle because there are less constraints about entries because of the non-commutativity. And this fact here is actually underlying, can be used as a tool to show, for instance, the result we saw a few slides ago by Helton and McCullough in the unconstrained case. This is also underlying the fact that there is finite convergence for the matrix hypercube or the matrix ball. So this is funny. In the non-commutative case, situation becomes sometimes easier to handle because you have more freedom in the moment matrix. So to summarize, so the quantum commuting value, as I have explained, it is formulated as an instance of non-commutative polynomial optimization, and hence it can be obtained as a limit of a hierarchy of STPs. And if the optimal solution of a given moment relaxation is flat, then the relaxation is exact. It gives a true minimum, and one can extract a solution. And this solution is finite dimensional, and actually then one finds not only the quantum commuting, but one recovers the quantum value. So in general, the quantum value is below the quantum commuting, but if one finds a flat optimal solution, then actually the quantum value is found. So this is, yeah. And so this NPA hierarchy has been used in practice by a number of authors. I just list a few authors here. I didn't give the exact references, but it has been used in practice for approximating the maximum quantum violation of Bell inequalities.
Monique?
Yes?
You have a question? So you mentioned finite convergence, exactness of the first level of the hierarchy, the case of matrix balls and boxes.
Yes.
And you motivated this by stating the theorem in the previous slide about the Falat extension. The fact that
one, huh?
yeah, this one, yeah. But so if you have additional linear constraints to the matrix ball and boxes constraints, it also converges at the first level, no? The hierarchy.
I think so. Yes. Yes. I put a bemol in my answer. I would have to check again what are the exact conditions, but I think that linear should be fine. Yes. Yes. Yes.
Or even quadratic as soon as the
but not all quadratics, Didier. I don't have clear in my mind now, but there are so the ball and the hypercube were really tuned in such a way that the proof would work through. It's not true for all quadratics, because if it would be true for all quadratics, at the end of the day, if you remember the formulation of the non-local game, of the optimization problem for the non-local game, it was actually quadratic.
Mm-hmm. Mm-hmm.
But we had this non-commutativity, this commutators constraints of the form AB minus BA equal to 0. And this was not okay to have this theorem.
I see. So in a non-convex quadratic case, what is the obstacle? So you mentioned this theorem, which is shown now, the fact that there is no additional constraints on the extension of the moment matrix to the next degree. So in the case of non-convex quadratic constraints, you have additional obstructions, or?
Then it would be another theorem. You have to work a bit more harder than what is shown on that slide. So what is shown, this theorem here suffices to show the Helton-McCullough in the unconstrained case. And in the constraint case, you have to work a bit harder and be a bit more careful, but somehow things just work. It's written in the lecture notes, but I just don't have it now. But it's written in my set of lecture notes.
Yeah.
But it's kind of a very happy situation that it works in the ball and the matrix hypercube.
Mm-hmm. I think there is a question by Kashgali on the chat. If you can open.
Can you? Maybe you can. Maybe Bernard can read me the question. I don't know where it's the chat. So. Chat is
just down.
No, but on my down there is no down.
Monique, hello. I'll ask?
Yes, please.
Myself. Is it known that finite convergence of this hierarchy in quantum case holds under some generic conditions on the constraints?
That's a very good question. I'm not exactly sure, actually. I don't know.
Okay.
Maybe Victor knows in the room.
Can you hear me?
Yes.
No, it's still open. It's still an open question.
It's still open, yeah.
Okay.
Yeah.
Thank you.
But there were recently a number of papers on non-commutative optimality conditions, because genericity in the commutative case was going along the optimality condition, showing that the optimality conditions for hold generically. But
So
this
they
is for, yeah.
that, but they still haven't succeeded to prove that generically finite convergence occurs.
Yeah, okay, okay.
But that would be a natural next step indeed.
And in the same order of questions, so is there something similar to the boundariation condition to get exactness?
There are a number of the situation is way more complicated, but there are a number of recent papers about extending the optimality conditions, and so maybe here I ask again Victor if he has a better answer.
I don't know. So it's this thing is precisely not proven yet.
I think it's safe to say that the situation is way more difficult.
Yes. Yeah.
But these are nice questions, nice open questions indeed. Yes.
Okay, thank you.
Okay. So then I am. Oh yeah. So okay, we have still a little time. So then I can. So two things I wanted to do till the end is showing how flatness goes, how the finite convergence on the flatness goes, and then would be mentioning a few extensions, but very briefly. So I think it's nice to now spend a little time to explain how the GNS construction can be used to show flatness, to show finite convergence on the flatness. So here's the setting. We have an optimal solution L to the moment relaxation of order T, which means that L is acting on polynomials of degree up to 2T. And L is flat, meaning it satisfies this condition. If you wish here, instead of this decay, just put a 1 for simplicity. And then the claim is that the relaxation is exact. So bound is equal to the minimum, and one can construct a solution of the original optimization problem, where the Hilbert space has dimension R, where R is the rank of the moment matrix. So how does it go? So first thing, one of the constraints was that L was non-negative on sums of squares. In other words, the moment matrix of L is PSD. So this moment matrix is indexed by non-commutative monomials up to degree T. So if you have a matrix which is PSD, then it is the gram matrix of a system of vectors. So any PSD matrix can be seen as a gram matrix of a system of vectors, which means, yeah, which is written here. So this moment matrix is indexed by words W of which are words in the variables x1 up to xn, and these words have degree at most t. This is what is meant here. And if this moment matrix is a gram matrix of vectors, so for each index row, we have a vector. The matrix is indexed by words, which means that to every word, we have a vector, which we call W tilde. And the property is that the entry of the moment matrix indexed by the words V and W is given by the inner product between the associated vectors V tilde and W tilde. So this is, and by definition, the entry VW of the moment matrix is given by evaluating L at the word V star W. So now we have a system of vectors indexed by the words. So the tilde represents a vector associated to the word. So we have a system of vectors VW tilde indexed associated to the words. Let's give a name to their span, H. So H is the span of these vectors. So it's a finite vector space. This is our H. And now we use flatness. So what does the flatness say? It says that the rank keeps the same when you look at the principal submatrix index by the words up to degree t minus d. Okay, up to this. So then this means that this vector space H is actually, you can also describe it as the span of the words of the vectors W tilde associated to this lower degree words. So this equality here is exactly coming from this flatness condition. So we have this vector space, which is actually spanned by the vectors associated with lower degree words. So again, just think of dk as 1, if you wish. Now we can define the so-called multiplication operators. Let's call them xi, so this is an operator which goes from h to h. And how does it go? We have to define how xi acts on a typical vector in h. H is spanned by those guys here. So we just explain how xi acts on such a w tilde here. So okay, I named it here v tilde. So if v is a word of degree at most t minus dk, then the action of xi on it will be, first you multiply the word with xi, so you get a new word, xiv, and then you take its associated vector. And this is well defined because xiv, v was degree at most t minus 1, so xiv has degree at most t. So it makes sense. So this is the crucial part where we use the fact that H is spanned by stuff which looks only up to degree t minus 1. So this is why we can define this multiplication operator. And now we have all the objects in hand to define the feasible solution to our original problem. So we have x1 up to xn, these n operators which are acting on H. We have H, which is finite dimensional. We have this x1 up to xn. And for the state psi, we take the vector associated to the constant 1 polynomial. And then it's kind of an exercise, but one can check. So one needs to check that this defines indeed a solution to the original non-commutative polynomial optimization problem. So the only thing you need to do actually is to check that the xi satisfies the constraints, which were asking that hj of x should be positive semi-definite. And this is where here you use this flatness condition up to this minus dk, which was the largest, highest degree of the constraints. But this can be done. So in this way, we get a solution to the original optimization problem. By construction, L of P is equal to the moment bound because L was chosen to be an optimal solution to the relaxation. So this is by construction, this identity, this equality. But L of P is defined to have this form. This is a property that we can check for the construction, that L of P is also equal to this. And then it means that this thing is larger than the smallest value P-min of the original problem, because the original problem was minimizing over all x and minimizing over all psi. And here also, so this value is at least the minimum. So this is by definition of the original problem. So now what do we get? We get that the moment bound is larger than the P-min, but the P-min is always larger than the moment bound. So the P-min is equal to the moment bound. So we obtain that the bound is actually exact. And so this is concluding the proof in the non-commutative case. We have obtained exactness of the bound, and one can construct an optimal solution. Here is this optimal solution. So the GNS construction is showing that Ondo's flatness the bound is exact, and one gets an explicit optimal solution to the original non-commutative problem. And nice thing to mention now is that we can also do this in the commutative case, in fact. And the commutative case can be seen as a non-commutative polynomial optimization problem, where you would add the constraints that xi xj is equal to xj xi for all variables. So it's a special instance of non-commutative optimization problem. And then if you do this construction here, then you see that these matrices xi, which I've constructed here, actually they pairwise commute because of the extra commutative constraints, commuting constraints that we are now adding. So they can be simultaneously diagonalized. And the eigenvalues are going to give actually the scalar solution to the original polynomial optimization problem in the commutative case. So what I am trying to explain here is that if you do this proof in the non-commutative case, then this also gives you a proof for the flatness theorem in the commutative case.
So Monique?
Yes?
What about the constraints?
The HJ constraints? So this is contained in the sentence show that this gives a solution. So there is something to show here.
Okay, thanks.
You need to show it, but I mean, it falls down. And as I said, why it will work is because we are saying that the rank of MT is equal to the rank of MT minus dk. So this is why we go deep down here. It's in order to be able to show that the constraints.
Yeah, okay, thank you.
And one tip is of norm 1, because you have
yes, you also want this thing is of norm 1 because yeah, it also follows. Yeah, okay. Now I don't see it immediately, but it follows from the construction.
From the constraint L1 and 1.
Yeah, exactly. Thank you, Bernard. Exactly. Yeah. Okay, so I think I'm almost to my time. I've maybe 2 more minutes, maybe?
Yes.
So then in these 2 more minutes, I just want to, I will flash then quickly about extensions of this non-commutative polynomial setting, which have been studied in the recent years. So the first, yeah, maybe let's just show it. The first other setting you could look at is, instead of minimizing the smallest eigenvalue, what you could do is minimize the trace of a polynomial evaluated at operators. So this is what you would do. Then you could design also a non-commutative, a hierarchy. So then your L, you would have to model L of P would be this thing. And you would have to what you could do is have additional constraints on your L, namely that it is tracial, meaning that L of Fg is equal to L of Gf. And this is because the trace of Fg is equal to the trace of Gf. If you have matrices, this is true. So you would add tracial constraints to your L and on the sum of squares side, you would add commutators to the quadratic module. So you can design a hierarchy of SOS and moment bounds, but the parameter is more difficult to approach because you can show that under Archimedean conditions, the hierarchies are going to converge to some value, but this value is going to end up in a way more broader setting of solutions. You will have to allow solutions in a finite von Neumann algebra equipped with a trace. So you really leave the domain of matrices. You have to go to way broader setting. But you can do this. There is a link between the tracial polynomial optimization problem and the Cohn's embedding conjecture, which goes via this tracial polynomial optimization problem, which was shown by Klepp and Schweighofer. yeah, so maybe in one sentence, this is the first line here is trying to understand what are the polynomials which lie in the tracial quadratic module of the hypercube. And these other sentences here are setting that the tracial, the trace of P is positive on contraction matrices on the matrix hypercube, on all contractions in a finite von Neumann algebra. So you may wonder, you have these three conditions which go about membership in the tracial quadratic module, positivity on contractions in a finite von Neumann algebra, and positivity on the matrix hypercube. And you may wonder, when are these three things equivalent or not? And what Kleppen-Schweigerhofer showed is that the Korn's embedding conjecture holds if and only if the membership question is equivalent to the positivity on the matrix hypercube. So this was open, but now it's disproved. We know that Korn's embedding conjecture doesn't hold, so we know that these things are not equivalent. But it's interesting to see, again, one link between polynomial, non-commutative polynomial optimization in the threshold setting with this widely studied Korn's embedding conjecture, which also relates to other conjectures in quantum information, all of them disproved by now. And that's the last slide. So non-commutative polynomial optimization can capture eigenvalue optimization, threshold optimization, but also more general objects like optimization of trace polynomials, where you want to model combinations of products of matrices and of trace of products of matrices. This has been done in a recent paper by Klepp, Magron, and Volchich. And even more general, so-called state polynomials, where you, instead of just having traces, you allow arbitrary states, not necessarily tracial. So this non-commutative setting, maybe the last sentence, opens up the way to many interesting generalizations. And these two papers also have applications to some certain problems in quantum information. So thank you very much for the attention, and sorry for being a bit over time.
Thank you. Maybe we have one or two last questions. Yes.
I wanted to ask about the non-commutative version of the positive Stellensatz. So when we talked about it yesterday, so this Puchina positive Stellensatz has the proof, like sort of from this real algebra, and I was just wondering what kind of goes into proving this certificate for the non-commutative.
So I didn't hear the last part of the question. So Puchina, yeah.
Yeah, I mean, it feels kind of different from the real algebraic geometry side. So I was wondering what theory is used to prove that certificate of non-negativity.
In the non-commutative setting, you mean?
Yes.
The original, I think the original paper of McCullough and Helton was rather algebraic, if I remember well. Yeah. So in a sense, maybe I'm going to say something which is a bit wrong. I don't know, but maybe the results in the non-commutative setting, some of them are way more difficult, and some of them are easier. And I would say it's like this analog of Puchina. I mean, so the Helton-McCullough is easier because you can get it via this flatness. So it has a proof on the moment side, which is a functional analytic proof. But this is not answering your question because you were asking about the analog of Putinar. So how do they? Yeah, I must say I don't remember just now how. This was again Helton McCullough who showed the analog for the truncated case under the Archimedean condition. So sorry, I just don't remember now how they did prove it exactly.
That's fine, thank you.
So, but these are nice papers. I advise you to look at them.
If we have no more questions, so thank you again, Monique.